Hi everybody, welcome to a new week of home learning. So first and foremost, I wanted to just let you guys know how awesome you all are and give you a peek at the calendar to let you know that you're almost done with home learning. What? No way. We're almost to the end of the semester, guys, and you're so proud of you for all the hard work you've been doing. So we're in this week. It is May 4th through the 8th, and today and this week, we're working on classifying reactions. We're talking a little bit more about the mole, and we're going to finish that mole packet this Friday. Next week, we're going to start talking about the electromagnetic spectrum, and we're going to finish out the semester. Come our last week day of school is on May 21st, so just a few more items on the list for you guys. It's going to be really fun. So this is what you have going on in this unit. Last week, you should have turned in your outline and your scientific notation activity. Today we're working on classifying reactions, which is 20 points. Then the second half of the week you'll work on your moles and chemical reactions quiz review, 15 points. And remember, all of these altogether, 75 points total in the test grade category. A really wonderful way to bump up your letter grade if you're looking to go to the next level. Some reminders that you still should be working on your PhET chemistry project. That due date is coming sooner than you think it is. So if you haven't done any of this, you are very behind. The entire project is due May 15th. It's going to be a 90-point lab grade. You should have completed all of the PhETs that I've starred: atom building, molecules, isotopes, chemical equations, reactants, molarity, and now you're working on choosing 2 PhETs of your own. I'm not going to assign them to you for these last 2 PhETs. I want you to pick any 2 in the chemistry category that you want more information on. So you see this on the bottom of your PhET sheet. You're choosing any of your liking. What you need to do is write the name of the PhET that you chose, still sign it, have your parents sign it, and you're going to do another one of those next week, and then you'll be done. So here's the materials you're going to need for today. It is number 3 in your take-home packet on the stapled together one that says classifying reactions in the mole. So you should have these 2 pieces of papers out today to take some notes. So here's our agenda. We want to understand different types of reactions, formula mass, and using moles to determine that mass. We're going to do some notes, and we're going to work on some practice problems together. So, we're going to start out with a little warm-up, get our brains rolling on science. True or false? So first one, the number of atoms in the reactant always needs to be equal to the number of atoms in the product. This is true. This is because both sides of your reaction, the reactant and the product, need to be equal. Second, the mass of the material on the reactant side needs to be the same as the mass on the product side. This is also true. You can't create mass out of nothing. So whatever mass you're making a reaction out of also needs to be the same amount of mass you have in a product. If you want to make 10 pounds of cookies, you have to have a total of 10 pounds of ingredients. This is true. So let's say you have a chemical reaction going on. Here in your reactants, you have 5 pounds of flour, 3 pounds of butter, half of a pound of sugar, 1.5 pounds of eggs. You create a chemical reaction that infuses heat, and at the end of that, you get 10 pounds of cookies. I like 10 pounds of cookies. I want that for sure. So, this all builds on a principle that helps us understand not only what a chemical reaction is, but moving forward, it's going to help us justify and divide up and categorize different types of chemical reactions, which is what we're doing today. We are classifying reactions, being able to put them into different categories based off of what's actually happening in that reaction. So each one of these types, these classifications, follow a specific pattern. You'll see spaces to fill these in on your note taker today. So the first type of reaction we're going to talk about is an addition reaction. This is when you get 2 substances that are combining into one. So if you were to think about this kind of formulaically, you would have 2 different substances, A and B. When you add them together, they combine to make a new substance called AB. A real-life example of this is the addition reaction of rust, where you take iron and combine it with oxygen to get this formula compound FeO3, which we actually see as rust. So rust is an iron oxide. It's usually a red oxide formed by the reaction of iron and oxygen in the presence of water or air moisture. So this chemical, it's pretty common because iron combines very rapidly with oxygen. So this corrosion is the chemical reaction where metals break down slowly because of other elements in their environment. Rusting, a well-known example of corrosion. It's the breakdown of the metal iron, and the reactants of this chemical reaction are iron, water, and oxygen. And the product is hydrated iron oxide, better known as rust. Rust, unlike iron, it's crumbly, orange, and pretty much useless if you're trying to build anything because it just falls apart. But rust is a really great example of an additive reaction where two substances combine into one. Our next type of reaction is a decomposition reaction. This is where it's the opposite. You now have one substance that's separated into two substances. Formulaically, this would look like you have substance AB that's combined together that's used to create A plus B. So an example of a decomposition reaction would be carbonic acid, which is H2CO3, and that's an ingredient in most soft drinks. A decomposition reaction takes place when carbonic acid breaks down to produce water, H2O, and carbon dioxide, CO2. This occurs when you open a can of soft drink and some of the carbon dioxide fizzes out. You can see the chemical equation reaction for this here on your screen. Our next type of classifying reaction is called single displacement reaction. This is when one element replaces another in a compound. So here's an example here. You have copper plus silver and nitrate. So you have silver nitrate additive there, and in the end, you kind of see in this equation as you're looking at it, the copper and the silver just switched places in the reaction. So you see copper, silver switched places there, now copper is attached to the nitrate. So why might copper and silver nitrate react this way? Well, let's watch this reaction happen. The copper is coated immediately with a black substance. After some time has passed, the silver nitrate solution transforms from colorless to blue, and a silvery substance then collects on the copper wire. When you react solid copper with silver nitrate, a redox reaction occurs, as shown in the equation. The solid copper reacts with the silver nitrate solution in the water to produce solid silver and copper nitrate. This is called a redox reaction. The copper gives up 2 electrons and transfers them to 2 silver ions to produce solid silver. The nitrate ions are merely spectator ions. They play no role in the net ionic equation. The black that immediately forms on the copper is probably copper nitrate that eventually dissolves in the water, thus giving the bluish color due to the presence of the Cu2+ ion. The silvery substance that collects on the copper wire is the solid silver that's forming. Our next type of classifying reaction is a double displacement reaction. This is when two elements exchange places to produce two new compounds. So here you can see when you have silver nitrate plus salt, and you actually see, here you can see the Cl switching places with the nitrate. And now you have your nitrate on your reactant side, it's attached to your silver, but on your product side, it's attached to your sodium element. So double displacement. You just have two elements switching places from one molecule to another. Next, we have combustion reactions. This is a type of reaction where you combine with oxygen to make a product of water and CO2. So an example would be a combustion reaction of methane, where you take methane plus oxygen and your products are water and carbon dioxide. You can also look at the combustion reaction of alcohol. This is your chemical equation for alcohol or ethanol. If you also react that with oxygen, you get a reaction of CO2 and H2O. So this is a whoosh bottle demo, and it demonstrates the combustion of alcohol vapors in the air inside of a polycarbonate bottle. The initial jet of flame and hot expanding gases gives you an idea of how energetic this reaction is. So much so that ethanol is used as a fuel for internal combustion engines in other places in the world. As an alternative to fossil fuels, ethanol has environmental and long-term economical advantages. Ethanol-powered and flexible fuel vehicles can run on a mixture of hydrated ethanol and petrol. This greatly reduces the consumption of petroleum fuels and also reduces air pollution since only water and carbon dioxide are produced. So knowing this information we know about classifying reactions, we're going to work through some of these reactions below to either classify them as addition, decomposition, single displacement, double displacement, or combustion. So I'm going to walk through a few of these together with you. So the first one, you have CO2 plus H2O gives us H2CO3. So we're combining a gas and a liquid. We get an addition reaction. This is kind of saying A plus B equals AB. All we did is combine the molecules we had before and giving us a combined total molecule at the end. Number 2, Cl2 plus 2Ki, and then you get 2KCl plus I2. This is a single displacement reaction. The reason being is that you see that the chlorine replaced iodine attached to the potassium on your product side. It's singly displaced, moved around the iodine, so now it's on its own on the product side. Number 3, you have H2O2 going to water and oxygen. This is a decomposition reaction. This is where we get AB reacts and gives us A plus B separately. Number 4 is also a decomposition reaction. Follows the same exact protocol. AB reacts to give us A plus B. 5, you see C6H12O6 plus 6O2 forms a reaction to give us CO2 and water. The second you see CO2 and water in a product side, that gives you an automatic indication that this is a combustion reaction. Number 6, there's a lot of elements to sort through here, but what you're seeing is the pairing of two different elements together, and what I actually see is that those pairings switch around with each other, which gives me the indication that this is a double displacement reaction, because the calcium and the silver are switching around on the reactant side to the product side. This is same with number 7, but this time you have sodium and copper switching around on the reactant versus the product side. We're displacing them. We're moving them, being attached from one molecule to being attached to another molecule. Versus number 8 is only a single displacement because it's only one of the elements that is moving. In this case, the only element that's actually moving is calcium. It's going from being attached to the chlorine to instead being on its own. And then the sodium attaches to the chlorine on the other side. Decomposition for number 9, because we're taking an AB and making it into an A plus B. And then lastly, we have number 10, a combustion reaction, which we get because our products are CO2 and H2O. Anytime that those are just our products, we know it's a combustion reaction. This information on classifying reactions will become very pertinent when you complete your activity later this week on your quiz review for reactions in the mole. We're going to move on today to a different topic about counting mass, but this involves something we learned last week called the mole. Now, if you remember, a mole is a unit of any substance that contains Avogadro's number of atoms of molecules. And Avogadro's number is 6.02 times 10 to the 23rd. And that just tells us how many atoms or molecule are in the mole of one substance. What a mole is it's a universal number that kind of makes an even playing field so we can look at how much of a substance we have in the unit of a mole. So this is what we're going to use to count formula mass. So let's say I have a substance, and what I want to do is find its formula mass. I'm going to do that by adding up all of the atomic masses that are listed on the periodic table for that formula. So let's start with something simple we're all familiar with. H2O, water. Well, first thing I want to do is identify how many elements are in that substance. What elements make up water? Well, I have hydrogen and oxygen. The next thing I want to know is how many of each element do I have? Well, I know in the subscript in H2O of my substance that I have 2 hydrogens and 1 oxygen. Next, I want to look up the formula mass. So for hydrogen, the top left part of my periodic table, I see a formula mass written there. The atomic mass is 1.008. I'm going to multiply that formula mass by 2 because I have 2 hydrogen atoms, which gives me 2.016. For oxygen, on the right side of the periodic table, my atomic mass is 15.999, and I only have 1 of these, so my formula mass is 15.99. My last step is that I'm going to add up both masses together to get my total formula mass, which is going to be 18.006. This gives us something called a molar mass. So again, the mass of a mole of a substance, we know that 1 mole is going to be equivalent to 6.02 times 10 to the 23rd molecules of whatever substance we're looking at. So when Avogadro came up with this system, he knew that he could set up the periodic table that if you multiply the atomic mass by 6.02 times 10 to the 23rd, we would automatically be able to convert atomic mass to grams in a perfect 1-to-1 ratio. So for water, H2O, my formula mass, my atomic mass is 18.006. This perfectly translates to 1 mole of water, which is going to be equivalent of having 18.006 grams. That's how many grams there is in 1 mole of water. And that's different for every substance that you're looking at. So this is the activity that you're going to be working on today. You're going to be working through different columns of this table to ultimately determine the molar mass in grams of different substances. I'm going to work through a few examples with you. So here, you have your first one. You have strontium. So I'm going to look on my periodic table. I'm going to want to identify what's the atomic mass for strontium. I then want to determine how many strontium do I have. Well, I only have 1. I'm only looking at 1 element. So what's my formula mass? Well, I didn't have to do any math there to figure out that 1 times 87.62 is 87.62. And with my 1-to-1 conversion, due to Avogadro's wonderful math, I know that my molar mass is 87.62 grams. Let's try neon. For neon, you get, if you're looking it up on your periodic table, you get the atomic mass here. I only have 1 neon, so I know my formula mass is the same as my atomic mass, and my molar mass is going to be that 1-to-1 ratio there in grams. Let's try one that's a little bit more complicated. I have CaOH2. So all the elements I have is calcium, oxygen, and hydrogen. I'm going to look up the associated atomic masses for each one of those elements. And then I need to determine how many of each one of those I have. 1 calcium, 2 oxygen, I know that because the OH is in parentheses, and 2 hydrogen. Then I need to multiply the atomic mass times how many of that element I have to get the formula mass for each individual element. My final step is going to be to add up all the formula masses to determine my molar mass in grams. So this is your activity for today. You're going to finish this practice, which is this third sheet of paper in activity 3, to calculate the molar mass of 1 mole for each substance. And this is going to be due by this Friday as a Schoology assignment, or you're going to email that to me if you can't get onto Schoology. So that's your lesson for today. We'll meet back again on the second half of this week for a mini lesson and get you ready to finish up this unit. Have a good day.